Good afternoon. My name is Fabricio Fernando Verdeja Palomeque, and I am a current student of Robotics and Telecommunications Engineering. And I'm going to talk to you about my professional practices project presentation, which is called Characterization of Microwave Components Fabricated on PCBs and Commercial 3D Materials at Cryogenic Temperatures for Millimeter Wave Astronomy Applications that takes place in the INAOE. First of all, what is the INAOE? The INAOE is the National Institute of Astrophysics, Optics, and Electronics, and it is a public research center belonging to the National Council of Science and Technology, also known as CONACYT, and is located in the town of Tonatzintla, San Andrés Cholula, Puebla. It is also a higher education center with certified quality programs in master's and doctoral programs that focus on astrophysics, optics, electronics, computational sciences, space science, and technology. The INAOE is in charge of the Large Millimeter Telescope. The Alfonso Serrano Large Millimeter Telescope is a single-dish movable telescope designed to observe radio waves with wavelengths between 0.85 to 4 millimeters. Its active surface area of 50 meters in diameter makes it the largest radio telescope of its kind in the world. The mission of the LMT is to perform pioneering research, to train future generations of scientists and engineers, to develop new technology for the benefit of society, and its main scientific objective is to study the formation and evolution of structures in the universe throughout its history. So now let's talk about my project. Keeping in mind the instrumentation needs of the LMT, it is proposed to study, design, implement, and characterize components in the microwave range that goes from 0.3 to 30 GHz for radio frequency and part of the millimeter range that goes from 67 to 110 GHz for radio frequency at cryogenic temperatures, which means temperatures that go down to 0.25 kelvins individually in two different ways. For the planar technique, devices made on commercial substrates with microtaping techniques, and for the volumetric, with polymer waveguide designs covered with tapes or conductive paint. So, what is the main objective of this project? Well, the main objective of the project is to define the best techniques and materials for the construction of microwave devices, and with the use of the 3D printer to innovate in the use of these materials in instrumentation. So, in other words, it is to study components in the microwave range and their performance in cryogenic temperatures through the design, simulation, implementation, and characterization of waveguides and filters, to innovate in the use of these materials in instrumentation with the needs of the Large Millimeter Telescope in mind, recording results using ANSYS HFSS software, 3D printing, and cryocube measurements for low temperatures. What are the main goals? Well, it is defined as goals to be achieved first to the design of microwave components in CAD SolidWorks and simulation in ANSYS referent to waveguides, combiners, and filters. Second, the fabrication of the design components through PCB and electronic techniques and the employing of the 3D printer. The laboratory characterization of the designs at room and cryogenic temperature by using different laboratory equipments, systems, and sensors, and to report the progress in an article. Since the project consists of testing waveguides and filters based on up to 8 GHz signals under cryogenic conditions that simulate void space conditions, the general specifications are listed as they are shown. For the cryocube desired conditions, we are looking for a pressure of the value of 1 times 10 to the negative 5 millibars, and a range of temperatures that vary from 300 Kelvin to 138 Kelvin. And the signals to be transmitted need to have a frequency up to 8 GHz. Talking about the waveguides, we need a coaxial adapter, conductive filament, and a range of frequency that varies from 5.85 GHz to 8.2 GHz. And for the waveguide filter, we want a range of filtering that goes from 7.03 to 7.32 GHz. Now it's time to talk about the development design of the project. So we've got first the ANSYS simulations. For the first one, we've got a 20 GHz waveguide combiner on the ANSYS simulation. This type of waveguide combiner is used to combine the output power of 2 times 20 GHz solid-state power amplifiers with compact size and low insertion loss. For the second picture, we've got a bandpass filter on the ANSYS simulation. As we can see, the colors represent the magnitude of the electric field near the conductors. The HFSS multipaction offers a resource-limited approach to vacuum simulation in space communication systems and vacuum electronics. And on the third picture, we've got a T-conjunction simulation. This composition divides an incoming microwave signal into 2 outgoing signals. The partition splits the signal, directs it to the output ports, and minimizes mediation on its access ports. Next, we talk about the PCB fabrication. As we can see in the pictures, first, the PCB fabrication process takes place cutting the plates on the desired sizes that were already specified according to the components to be tested on the cryostat, and we get the circuit schematic design on KiCad. For the next picture, we get that the circuit schematics were printed on the thermotransfer paper after verifying the sizes matched the size of the plates. Then, the plates are located inside a petri dish, and the dish is placed over an iron preheated at 40 degrees Celsius, so that heat will accelerate the reaction, and we get plates that have a better cooling effect when testing them under cryogenic conditions. Focusing on the main project, we talk about now the cryocube testing. As we can see in the pictures, we get a waveguide screwed with the temperature sensor. The 2 coaxial connectors are linked to the device, as we can see. Then, the cryocube is sealed, placing the upside surfaces, the radiation shield, and the upper surface. Next, with a helium hose, the gas is blown to the several parts of the cryocube that might have had a leak, and we identify those leaks. Using nail polish, we get a new protective layer that is added so that the identified leaks could be sealed, and the cryocube is noticed to have several pollutants presented on the faces, which causes pressure and temperature to lower much slower than prevented. Then a cleaning process takes place. Now let's talk about the results. The vector network analyzer was set to test frequencies ranging from 4 GHz to 8 GHz with a bandwidth of 10 kHz. This test was conducted to check if the outputs were the same as the ones obtained previously under average temperature and normal pressure. If so, the testing will include the 2 waveguides developed and several frequency filters. The testing on August 22nd with normal conditions, which means 24 degrees Celsius and a pressure of 1.01 millibars, presented a value of minus 2.61 decibels at 7.1 GHz, while the test under cryogenic conditions, which implies 138 Kelvin and a pressure of 1 times 10 to the negative 5 millibars, presented a value of 4.12 decibels at the same frequency. If the pattern of reflection varying this frequency remains similar, it is true that there is higher reflection on the transmission with cryogenic conditions. However, this might indicate that there is a test needed to complete to check if the values remain unchanged at normal conditions before introducing the devices into the cryocube. As we can see in the pictures, there are more pronounced peaks and troughs at cryogenic conditions. So, if considering these are only the caps and there is no filtering process taking place, the transmission line should be at a constant value with much less variation than the presented on the most recent testing. And finally, we get the double-sided copper bakelite plate that is ready for cryostat testing, which can also be used to do a research about quantum computing. Now for the conclusions, as it can be observed, the final deliverable is product of the knowledge acquired through the lessons of the training. The ANSI simulation allowed to analyze the behavior of radiation spectrum and power, gain and loss of the transmission, and direction of the output and input reflections, which is the focus in here. The training was critical to comprehend the relationship between waveguide design, filtering, and transmission under different environmental conditions, such as temperature and pressure. The sizes of waveguides and filters, as well as the materials, are important parameters to consider. Therefore, a further analysis, taking into account efficiency, opportunity areas, connections, and finally specifications is required. And we can also say that the laissez-faire leadership helped organize better, since time was defined by the student. Finally, we get the references and of the articles that are the basis of this research. Thanks for your attention.